Hello guys, welcome to another episode. In this, uh, I'll to bring up the moisture sensor basically. I will integrate it with OLED later. First, let me just check and experiment with the moisture sensor. So for this, firstly, I'll just copy the hello world directory. Mm, just a sec. ESP32. For this, I'll just go to. I'm already in the ESP I'll just go to navigate to examples, and in this dir I'm going to this get started directory. cd get started. Okay, just a second. Sorry, my bad. What happened? Oh, it's not an underscore. Okay, now in this directory, as you can see, there is this hello world directory. This is what I intend to copy and create a new project with it. For this, I will be using this command basically. So basically here I will be just copying this directory uh, to a new directory. Where is my, so for this basically I'll be just copying this new directory where this e ensures that directory and subtracting empty ones are copied, and I basically treats the destination as a directory. So once I execute this command, oh yes, the after running the command I've copied and my directory has been created with all the file of hello world example being copied here. So first we will just navigate to the directory first. Okay, now I'm in C folder. I will just navigate to the directory C users cd esp and now cd moisture. So I'm inside the directory. In the directory, let me just check. cd in, I will just cd into main, and let me just check again. So this is a hello world file. We will just open this file code and replace the code. Okay, so this is the code in the hello world file which we are going to. I have already generated a code and did some corrections. So I have generated the code using ChatGPT. So firstly I'll just paste that code. I'll explain the code later. So here I have pasted the code. I'll just explain it later. First let's see its functioning. I'll just save the code now. Okay, now I'll just go back to the main folder. Now I'll just run the commands and flash the ESP. I'll just use the menu config. It's okay. Now I'll choose the build to build the code and check if there's any errors. Okay, now I'll just flash the code. Okay, my combo is 4. Now we will monitor it. So for monitoring, first let me just put the moisture sensor inside the soil. Just a sec. So as you can see, there's a dry soil and a wet soil. First we'll put the moisture sensor in the dry soil. And let's monitor now. Again, as I mentioned, comp 4. So in the dry soil we are getting 15, 17, 25% moisture level, 26. Maybe I just need to put it inside. As you can see, okay, now it's not detecting any moisture. Sensor is local sensor maybe, so I don't know why it's increasing. Detecting, and it's continuously increasing. I don't know why it is detecting basically 100% moisture, but let's just check what's the issue. I don't know why it was detecting moisture earlier. So as you saw, it is 0% in dry soil, and as I put it in wet soil, it will increase. As you can see, it is increasing. Basically the sensor is not that costly, so I think it will react like this, but still it is sufficient for a home project like this. So as you can see, the moisture level is increasing. So let's, okay, as you have seen the demonstration, now let's just stop this and focus on the code. Now let's just go back to the code. Oh, so this is the code. Firstly, we are using this library stdio. For this, okay. So next we are using this free RTOS library. Support. Basically, we have used a function, a delay function, to give delay between readings. So for this, we are using this. Same here. But we have not created any task or something. Just it is basically integrated with ESP, the RTOS. So it is, so we can directly use this delay function. Okay, then we are using ESP system.h file. It basically grants system level functions, ESP32 chip information system report capabilities. Then we are using driver adc.h. Basically, since we are using analog to digital converter, this is for enabling that. Then we are using ADC cal. Basically, before using the moisture sensor, we need to calibrate, so this helps in that calibration. And in types is basically ensures a precise integer representation. Basically, you will face issue here if you are not using that in type.h file, since we are using different types. So for that, okay, firstly is we are setting a default voltage reference. In case the chip doesn't have its own calibration reference values, it can use this. But since our chip is already integrated, this called something called fuse, which basically helps to calibrate the ADC sensor. So since this I have checked already, it has that, so there's no need for this line. If you don't want, it's okay. So for each reading, we are giving we are taking an average to reduce the noise. So we are taking 64 samples for each reading again, and we are using GPIO port 34. Before this we continue, I'll just show you the connections to connect ESP32 with capacitive moisture sensor. So basically, this is the wiring one we are talking in the capacitive moisture sensor. There is VCC, ground, and A out. So basically, we are connecting VCC to 3.3 volts, down to ground, and A out analog pin to GPIO 34. Okay, so this is the connection. So now let's just focus on the code. Okay, so earlier I have defined this is the minimum voltage value in which, and this is the maximum voltage value I am getting in wet soil, this is in dry soil. So I'm taking this as a reference. These are basically benchmarks. So now let's go here. Here we are basically configuring the ADC's width and attenuation. This is I have taken as 12-bit. This is the maximum width we can do. The sensor becomes quite precise. And attenuation, ChatGPT suggested 11. So I have taken 11. Basically we're using 11 dB since it extends ADC's measurable voltage range to its maximum, enabling the capture of a wider range of signals. This is particularly useful when you're dealing with varied environmental conditions that might cause the sensor output to fluctuate significantly. If the soil moisture sensor's output voltage can go beyond the ESP32 ADC's direct measurement capabilities, for example, if it outputs voltage higher than 3.3 volt under certain condition, the 11 dB attenuation setting allows for those higher voltages to be measured accurately by scaling them down within the ADC's input voltage. Though choosing 11 dB attenuation inherently involves a trade-off, while it allows for the measurement of higher voltage, it also spreads the ADC's resolution over a wider range of input voltages, potentially decreasing the resolution of image. This trade-off is acceptable in many applications where covering a wide range of case. So basically it is saying that we have chosen 11 dB sometimes because the highest voltage that it can generate can go beyond a certain level, so higher attenuation helps in measuring those voltages as well. So it is good for iron, so that's why it suggested that. Okay. So firstly we are configuring the ADC channel, then basically these two lines, this and this, is basically calibrating the ADC sensor, the ADC inside the chip. It is using a data already fed into the chip, calibrated. So this is the general command. Basically we are using calloc basically to give a memory or heap to this ADC catch pointer, and the size of the heap is this. Okay, one is basically there is one channel. So now in this calibration we are using ADC channel 1 because we are using GPIO 34, and so for that ADC unit 1 channel 6 unit 1. So you can check this in the ESP32 pinout diagram. Okay, so for then we have defined a variable of ADC reading. For here basically we are adding all the readings, all the raw data that we are receiving of 64 samples into this ADC reading. This is the channel which we are data we are receiving, and okay, channel 6. Now we have just dividing the ADC with number of samples, and also we are converting this ADC reading to a voltage level. For this we are using this ESP32 cal underscore raw underscore 2 voltage. Is already defined in ESP32. Here basically we are converting this voltage to moisture percentage. So basically if the voltage is below the dry soil or equal to dry soil, moisture percentage 0. If it is equal to or greater than wet soil, moisture percentage 100. And this is the calculation for moisture percentage. Basically voltage minus dry soil, voltage into 100 divided by wet soil minus dry soil. This is a common percentage calculation, and after that we are printing the results, and then we are putting a delay. So this is the whole code for this. So now since this is also working, now in the next video we will just try to display this moisture percentage on the OLED.